Good afternoon, gentlemen. I'm going to go through all the topics that we discussed in Unit 6.5. In the description below, there are timestamps so that way you can hop to each of the subjects, but hopefully this helps you be successful for our test. So let's get into it. The first topic we're going to talk about is electronegativity. Electronegativity, by definition, is the ability of an atom to attract electrons when bonded in a compound. Now, typically, the one that's going to have that higher electronegative value is the one that has the most valence electrons. So, for example, if I had magnesium and oxygen, my oxygen would have a higher electronegative value because it has 6 valence electrons, meaning it's closer to 8. Whereas magnesium has 2, so it's not really going to want those electrons as much as oxygen. We use the electronegativity values as just a way to see which one really wants electrons. And we show this by using the number between 0 and 4. These values range from 0 to 4-ish, and as you can tell, there is a direct relationship with these. When I talk about electronegativity, as I move from left to right, I'm going to see an increase in my electronegativity. So think about comparing lithium with fluorine. Lithium is at a 1, fluorine is at a 4.1. 4.1 is bigger than 1, so right there I can tell you that fluorine is more electronegative. Now when I look from top to bottom, I'm going to see a decrease. And right again, we could just look at our fluorine, which is that 4.1 compared to my AT at the bottom is a 2.0. Now it doesn't show that it's always a decrease because it may plateau at certain points. However, you should be able to see these general trends. The transition metals are the exception, but what you need to know is as I move left to right, I see an increase, and as I move down a group, I'm going to see a decrease. The next topic we're going to talk about is polarity. Polarity and bonds are the idea that electrons are shared equally in our covalent bond, but they can also be shared unequally in that compound. So when I say nonpolar means that they are shared equally. This is just the relationship we're going to see, and it's typically the ones that you can see between similar electronegativity values. So an excellent example of this could be a carbon and a carbon, or even an oxygen with an oxygen. Polar bonds, however, are when they are not shared equally. And this is where I see that difference in those values. So an example of this could be a carbon, a carbon and a fluorine, or even a carbon and an oxygen. In this case, it's where the electrons hang out towards the element that has the most valence electrons. My polar, those are my unequally shared ones that are in the atom. So as kind of stated before, this is where I see where I have an electron-rich region versus an electron-poor, and it's between those electronegativity values that we can tell. When I say polar, what you want to know is that the electron's going to spend time around that one element that has the most valence electrons. It's the closest one to my 8. And the reason why is it wants those electrons. And you can use that electronegativity periodic table to determine which one's greater. Based on how you solve for the electronegativity, this is how you can tell your bonds. So between 0 and 0.4, you're going to see a nonpolar. That's where my electrons are shared equally. Between 0.4 and 2.0, it's where they're not shared equally. It's my polar. And anything that's greater than 2 is my ionic. And remember, this is my positive bonded with a negative. To solve for this, you're just going to take the two electronegativity values and subtract them, and that will give you what bond you're working with. So in this case, if I have a 3.1, I'm going to see that that is greater than 2.0, less than 4.0, meaning that I have an ionic bond. And this works for all different types of elements. So just to sum up, to be a polar bond, the electrons have to be shared unequally. One is greedier. It's always going to be where my delta E is between 0.4, 0.5 to 2. And you're always going to be able to tell which is the more electronegative particle or element. To be a non-polar bond, electrons must be shared equally. My delta E is between 0 to 0.4, and the shared electrons are spending equal amounts of time on both. There's not one more towards the other. You can also determine polarity of whole molecules just by looking at them. Polar, you're going to see unsymmetrical lines. So for example, while this one would be considered a line of symmetry because I can pancake it and it's the same on both sides, this side would not be. And that carries through with all of them, where this would be a line of symmetry, but this would not. This could be a line of symmetry, but this is not. So anything that's not symmetrical is a polar molecule. Non-polar molecules are going to be symmetrical, where if I pancake, it's no matter what, I'm always going to see equal on both sides. So there's some lines of symmetry for you. The next topic we're going to talk about is solutions and mixtures. As you recall, there are 3 types of mixtures we deal with. We deal with our pure elements, where I only have one type of atom. We have our pure compounds, where I have only one type of compound in the mixture. And then I have my mixtures, where it's more than one type of compound or element that are mixed together. Pure elements only contain one type of atom. They cannot be separated, and these are ones that I'm going to find on my periodic table. I can have individual elements, or I can have what are called diatomic, and that's just where I have 2 of the same element bonded together. These are typically my gases. The next one I will see is my pure compounds, and these contain more than one type of atom, but they are bonded together. These can be separated with a chemical change exclusively, and these are always like magnesium chloride, sugar, water. I'm only going to see one type of compound in this mixture. Next, I see a mixture, and this is where I have more than one type of compound and or element mixed together. These can be separated physically. Great examples of these are pizza with no toppings, salt and water, colored M&Ms, milk. In chemistry, I deal with 2 types of mixtures. We have a heterogeneous and we have a homogeneous. Heterogeneous is where I can see the different substances that's not uniform. So an example of this is like pulp and orange juice, sand and water. It's where I'm going to see my layers in a way. So think about like oil and water. When I mix those together, even if I shake it up, it's going to separate out. So those are heterogeneous. Homogeneous is when my molecules are uniformly spread throughout. And what's important to note is that these are like Kool-Aid, salt, water. It's considered any solution as long as they're the same state of matter. Or I can have where something dissolves, then it looks like the same state of matter. That's when it would be considered homogeneous. Now we do have some special mixtures that are important to kind of note. They are called colloids and suspensions. Colloids on the macro level are homogeneous, but if I put them under a microscope, they would be heterogeneous. The reason being is it can scatter light. A couple examples of colloids could be milk, it could be jello, pearls, a lot of that stuff. Suspensions, however, those are heterogeneous because we're going to see clear defined layers or large particles suspended throughout. These are always temporary. So an example of a suspension could be your blood, that when my blood comes out of my body, it looks red. But if I let it settle, I would settle down into my platelets, my plasma, my red blood cells, my white blood cells. I would have all these defining layers to show me that my blood is not a homogeneous solution. So even if it appears to be homogeneous, it could be just a suspension. Now anything could seem like a suspension, so I could put salt water out and say, Mrs. McCaslin, the salt's going to come out of the water. But in that case, if I let something sit long enough, the water could evaporate away. So it's important to know that suspensions are temporary, but it shouldn't take you more than an hour to see those layers extend out. So a suspension is a mixture in which particles of a material are more or less evenly dispersed throughout a liquid or gas. So right here, before I settle, I mix some clay and some water together. So it kind of looks like chocolate milk. Now, if I let my clay and my water settle out, that is when I would see my clay settle to the bottom, my water on the top. So this would be an excellent example of what a suspension is. That even if I stir it and I stir, when I let it sit, it will create those separate layers. So to quickly review, homogeneous does not have layers. Heterogeneous does have layers. Colloids do not have layers. Solutions are homogeneous and suspensions are heterogeneous. Next, we're going to talk about solutions and solubility. These are the terms that you want to know with solutions, where my solute is my smaller amount, and that's usually my solid. So an example of this could be salt. My solvent is always my larger, and an example of this is water. And 9 times out of 10, it's going to be water when I ask you. Excuse me. Now, the next one is dissolving. Dissolving is when I'm mixing a solute and a solvent into a solution. So, for example, when I put salt in water and I stir it, my salt will dissolve. We got a chance to see that in our lab. The next words that you want to know are saturated. Saturated is the point at which no more solute can be dissolved. So remember, we saw this when we did our salt and water lab. I know not everyone was able to see that, but once you reach that max concentration, the salt will stop dissolving and it settles on the bottom. The other topic we do is unsaturated. Unsaturated is when I can add more. So when you add salt and water, if you don't have any salt that's coming at the bottom, then you can still add more. That's what unsaturated means. Right here is kind of a visual what we just talked about. Unsaturated is where I can still add more. Saturated is when I can't add any more, but if I do, then I will get what's at the bottom. And that's always an undissolved solute. The next thing you need to know is the concentration equation. This is extremely important that you have it down. If you do not know how to do the calculations with this, it will be a struggle on your test. Concentration is always the amount of solute in grams over the amount of solvent in liters. If I wanted to increase my concentration, I would increase my solute, decrease my solvent. If I wanted to decrease my concentration, I would decrease my solute and increase my solvent. But if you need to write anything down from this slide, please make sure that you have this down on your periodic table. It's important to remember that we're still going to have unit conversions. Your unit conversions can go from like kiloliters to liters, milliliters to liters, kilograms to grams, and milligrams to grams. So you want to make sure that you're always operating in the unit that the equation asks for. The next equation you want to know for a fact is my percent composition. Now remember, with percent composition, it is a little bit different. You're always going to have your grams of solute on the top, but now you're extending where you're going to have your total grams of solution. This will always be my solute plus my solvent. And typically water comes in milliliters, so as long as your water is in the units milliliters, you can easily convert that to grams. So an excellent example is if I had 10 milliliters of water, I could say that that is 10 grams of water. This conversion will only work with water, but I will give that to you. What you need to make sure is that you're always operating in milliliters when you're working with this conversion. And last but not least, let's discuss solubility curves. By definition, solubility is the ability of a solute to dissolve in a solvent. Now, solubility will depend on the attractions between the solute and the solvent, but we can have other outside forces coming and applying on them. An excellent example of this is temperature and solubility. When I'm working with a solid solute, so an example is like salt, maybe sugar, stuff like that, my solubility will increase as temperature increases. This means I have a direct relationship. If you recall, a direct relationship is always going to be where one increases, the other increases. So my solubility will increase as temperature increases. When working with this, it is important you know how to do the calculations. I will always give you a chart when we're doing this, but essentially what you're going to do is if I have a saturated solution of sugar and water, and I ask you with two different temperatures, you should be able to tell me how much is precipitated out. So for example, in this first one, it tells me that I'm working in a sugar and water solution. So I need to look at my sugar line. It gives me two temperatures. It gives me 80 and 40. So we go to 80, and I go up to my sugar line. And right away, I can say that's about maybe 360. That's 360 grams. Next, I go to my 40, because that's my second temperature. I go up to my line. I say maybe that's about like 240. And I can say, when I subtract them, that means I have about 120 grams of sugar that comes out. You should be able to do this with any type of line. And that's all you need to do for that calculation, which makes it a lot easier. Now, in contrast to solids, anything that is a liquid and gas will have a different type of relationship. So gases could be like CO2. Liquids could be maybe doing like acid. My solubility is actually going to see a decrease as temperature increases. And the reason why is that the kinetic energy of my molecules and how fast they move, in a gas, they're going to move a lot faster as that temperature increases, meaning they're going to leave that solution. So that's why I'm going to see a decrease in solubility. This is my indirect relationship. So again, as X increases, we're actually going to see a decrease in my Y. So right there, that's everything you need to know for our 6.5 test. Please make sure that you are working on the review guide, as this will help you be extremely successful on the test. But if you have any questions, please email me. Other than that, I hope you have a great day.